system. If you run the global model, you require observation from all over the globe. And evolution of this slide, it shows the evolution of observations, and it started from a late 18th, early 19th century. And major boost came in 73 when satellite data started coming. Satellite data is started coming, and 1973 many appeared, and this data volume increased exponentially. And if you see this one, data collection system was implemented at NCMWF for receiving various data sets through GTS, and from all over the globe with the GTS, the data started coming, and up to 2015, the data volume what we received at India is very, very less. And with the intent of internet and other services, the data volume increased tremendously. For receiving the bulk satellite data, NCMWF established a link with the NOVA servers at USA and started getting the satellite data in buffer format in 1998. That is the starting when we started getting the GTS, other than GTS data. And around 2018, we established a UMETcast reception system at NCMWF by using the NKN and European NEON link, through which multicast data processing system has been started coming to India. And we're getting all the data, almost every operational satellite data of WMO from various countries. We have started receiving that one. You can see the volume of increases in the pie in this chart things. And at present, we are receiving more than 500 petabyte 500 GB data set from various countries. And from India also, we have the satellite data from ISRO stations such as ISTRAC, NRSC. We started getting the data. India is the one country which is having both NWP system as well as satellite data plans also. With that, for NWP purpose, India launched many satellites such as INSAT, OceanSat series, and also with the help of international, especially France, we have the Solar Altica and Megatropics data sets. And we started many such satellites, including RESAT, Kalpana, and these data sets started using for NWP purpose. And if you see that one data reception things, we for receiving the data and real time, we have to monitor. We have the proper monitoring system to get the data. And so at NCMWF established, you can see various data sets where we are getting within 2.5 hours for running the assimilation NWP system that has been monitored regularly. And this is the monitoring system which we see the data reception is properly receiving or not. And for the satellite data, it is required to see the calibration of a sensor, because when satellite is launched, it is autonomously running, revolving the Earth and giving the data. So it is required to see whether sensor or calibrated, receiving properly getting the data or not. And we see in the case of megatropics data, we are monitoring the data quality by seeing the difference between the first guess and the satellite radiances that we receive. You can see sometimes the calibration issues are evolved, and we immediately notify the satellite agencies to rectify that one. And you see around November 19th or so in this chapter, data quality is the problem was noticed, and it was notified, and it was rectified, and like that the maintaining the quality of the satellite sensors has been has been taken up always. And for processing the new technologies also for satellite sensors are been are coming, that such as AOLS winds from the ADAMS satellites, and also GNSS radio occultation data. The new technology is coming, that one. In that, the data, the observations what we receive is not traditional what we do, that temperature, humidity, such sensors. What we'll get is a delay and bending angle in the case of occultation satellite. And in the case of ALS, what we get is the horizontal line of sight of wind. That is, it is not a wind, but it is a wind, but the wind is observed through a look angle from the satellite, as shown in this figure. And the wind is not a traditional wind, what we get as a wind vector U or V components, horizontal components of the wind. So, but to assimilate, to use such a type of data, we have to develop observation operators. What is an observation operator? Is it will a physical relation based on the physics of the observation. So, for example, if we take total precipitate water, what we get from the GNSS data, this TPWC is the we will get from the GNSS server. GNSS satellite. But in the model, we will get T, U, V, Q. These are the model variables, that is temperature, horizontal wind, humidity, that things. And by integrating the humidity, and we'll get the TPW. That integration is the operator. Like that, operator has to be, for every observation, the operator has to be built. And these operators will convert model variable to observation. And with observations, we can generate innovation. What is the change in the observation? The change in observation usually the NWP data for using in the simulation cycle and get added to the first guess parameters to get the proper value. In this way, we can handle new satellite data. For example, this is the operator for the horizontal wind. We can say that HLO is related to the horizontal wind U vector, V vector with azimuth angle of observation. Like that, a bending angle is related to the refractive index from the that is coming from the GNSS data. Like that, operators have to build to assimilate the new satellite sensors. This work we has taken at NWP centers for assimilating the thing. Like many data sets are coming like that, and now we have the models. NWP models are to different types of requirement of the data is required various formats. So data pre-processing system has to build the data from the whatever the format it is available to bring it to the data that is being used in the model, your assimilation and model systems. This pre-processing system is an integrated part of the NWP system that has to be implemented and developed for using in these models. And like that, when the data set is available, the next step in the NWP processing is the data assimilation. This data assimilation methods dates back to L.A.R. Richardson and this simple interpolation ability, where the data operators are not available at that time. And these things are up 1954. These data sets are used where interpolation techniques, and based on that one for NWP, that optimal interpolation technique also developed and being used in the data assimilation. In that type of scenarios, we are not able to use the satellite data directly with them. They're used to assimilate the data by deriving the temperature, humidity, and wind data information to that one. That is being used in that models. And with that, while derivation, we have the error generated in the retrieval process. So to handle that one, becoming a much more complex system, and we're getting the analysis, correct analysis is a big problem. After that, the variation analysis systems came into the picture, in which what I told earlier, like that analysis cost observation operators are being used, in which observations are model variables are converted to observations, and innovations are being computed, and using the cost functions, variance assimilation methods, data initial fields are computed, and this assimilation is called variation and assimilation schemes. In this variation and assimilation schemes, we can use the data satellite data, other remote sensing data, and other non-conventional data other than temperature, humidity, other than model variables. We can use the data in their native format by computing by computing the innovations. And the after these 3D war techniques, they developed the 4D war technique in which observations are computed, simulated at the time of observation, in which the model has been analysis systems are carried multiple times by using the adjoint models, etc. In this way, that hybrid and 4D war methods are being generated. At present, at present scenario, there are ensemble these 4D simulation methods and hybrid data simulations systems are being used, and India also, and we are starting using 4D NKVAR in the one of the systems, and 4D war ensemble systems in the based systems. And this hybrid methods, what we need to do is we are computing the model guesses based on the climatology by giving a weightage to climatological background errors and to the flow dependent variables. And this is the scenario which we arrived using the multiple ensemble members for assimilation purpose. In this, you can see the GEFS system that we are being done at NCMWF, in which 80 members has been used for ensemble members are used for the developing the flow dependent covariances, and they are used by giving a weightage to them and 25% to the coefficients to the traditional statistical generated methods, and giving the high resolution analysis, deterministic analysis being created. These ensemble are recentered always towards the deterministic analysis. Like the analysis has been created this cyclically every 6 hours at 0, 6, and 12 and 18 hours. We are getting the hybrid analysis system. This system is being now operational, and like that analysis systems has been developed. And if you see the development of these systems, basically if you see the development of NWP system, they're based on availability of the computing systems. You see in 1994 we implemented this T80 L18 model. That is an operational first time using that SSI statistical interpolation technique on Cray XMP YMP system, and this system was continued for quite a long time, about 12 to more than 10 years at the same format, and various efforts are made that time. This system is basically a complex system with the Cray dependent libraries and things, and lot of efforts are made in India to make the system to ported on various computing systems that are available, that are developed at India at CDOT, CDAC, NEL, BRC, etc. And these efforts are going on. And another thing at NCMWF, efforts are on to improve the forecast system in the same system by implementing new physics such as radiation schemes, Dr. John, and boundary layers by Dr. Swati Bose. Like that, scientists are working on improving the same system by improving the assimilation system as described earlier, and models physics by physical parameterizations and etc. That type of efforts are made up to the about 10 years. That type of work is going on. But after around 2006, Ministry of Sciences was formed. After that, the strategy of model development has been changed, and we quickly adopting the new models that are being available, that are developed elsewhere also to get the improvement in the forecast, such as T254 that was implemented in the Cray-XNE Param system in 2006 at NCMWF. Beginning on that one, various systems has been very regularly, the computers are being updated, various computers such as IBM P6 and Cray XE40. Many systems have very quickly, the computer system has been updated. With that updation, we are able to handle complex models and analysis systems. And hybrid analysis system has been implemented in 2016. And this with this we entered in the phase where ensemble forecasts are also being generated, are also made possible. And we entered using, instead of single deterministic forecast, we started giving the probabilistic forecast, etc. And systems have been available in June with implementation of hybrid analysis systems. And around 2012, another forecasting system based on unified model also simulated. If you see this one, earlier we are using the deterministic forecast, which is the single forecast method, where the forecast is given, definite forecasts are given, and we know the errors in the forecast because of various parameterization schemes that are involved. It is not, and we know that forecast errors. So to get into the correct picture, how much the forecast is reliable is possible by using the ensemble prediction system. And with implementation of hybrid analysis, hybrid variation analysis systems, it is possible to get ensemble forecast at desired resolution, so that will give the probabilistic forecast as available. And India, first we started the probabilistic, this type of ensemble forecast right in 1996 itself, with combined work of the Gopal Iyengar when he visited Kalane lab and started this work. The first system was implemented in that is GEFS 192L28 in 2014 itself, where the lag with the 20-member lagged initial conditions are used. That means we used the some forecasts that are generated at earlier cycles. With the cycles, we are getting the 20 initial condition by the breeding technique, and that are being used. This is the initiation of how we started ensemble forecast in 2018. But after implementing hybrid analysis system, we are getting the members lagged not at the real time, with about 80 members in the case of GFS system and 22 members in the other NGFS system that is implemented, that is being done at NCMWF. So we are getting the two complex systems with high resolution ensembles at 12 kilometers, which is highest in the world, and we are getting a 10-day forecast, and these are being given. We started entered in the hybrid using hybrid assimilations. We started giving the forecast in the probabilistic sense. And in the case of cyclone, we can give the number of the tracks, with all possible numbers are being we should get the number of tracks, and with that we can generate the strike probability. And instead of giving the definite where the cyclone is going to strike the land, cross the land, we can give the probability crowd, striking probability, and this will help the planners to how much area they can have to the highest probability where they have to concentrate for the evacuation, the possibility also, and where most probably it will occur. Highest probability is there. This information is available to the planners, so they can plan evacuation depending upon the probability and take precaution on that one. Similarly, with implement with this high resolution ensembles assimilation systems as in place, and in the start of monsoon mission in 2018, we entered other, not at IITM and other places. They started uh, seasonal forecasting as a system. This high medium range forecast analysis system start giving the initial conditions to these hybrid systems, such as extended range forecast system, coupled forecast system, that is put at IITM, and also ensemble forecasting system for that one analysis, ensemble initial conditions. These are started. These are being generated from the uh, medium range forecast analysis system that is run that is operationally run. These are giving support to these other systems, and also to the short range forecast that is given, that is developed at WRF systems at various various labs in India. For that system also, the initial conditions being generated is supported by the system. And at our system organizations in COAS, they started GODAS and ocean analysis system by using the analysis, this particular initial conditions that is generated in the model. And for forecasting, HWR system also plays various systems. This means for various purposes, we have the different systems in place, and they are supported by the global system that is run at global medium range forecast system at run at different labs. So different models are being used for different purposes, and this complex system is used for the forecasting at different levels. And to make this complexity much more simpler, and a seamless forecast system was established at NCMWF with the partnership of by collaborating at various modeling consortium, and we developed with this same model framework, starting from the high resolution 330 meters to the coarse resolution highest seasonal forecast system. All complex systems has been based on same dynamical core has been established. This is the state of art systems that is being used at present in the world, and even GFS system also is going to in recent period shifted to this type of complex this type of unified modeling frameworks. And at NCMWF for medium range forecast, global 10 and 24 and 70 levels system is being placed, and these various systems are being has been seamlessly running, giving a seamless forecast to the various purposes. For example, like this 330 meters for a fog forecasting and city-based forecast system, and medium range forecast of 72 things for high resolution forecast for city short range forecast, and 12 kilometers global and forecast, including deterministic and probabilistic forecasting system, and sub-seasonal forecasting with 64 kilometers coupled model system. And this complex system has been implemented a lot. And with the implementer systems and various physics and efforts are also on to improve the physics in these models by implementing various physics schemes in that one. For example, in the recent system, we have been implemented cloud erosion interaction microphysics at CASIM, and also bimodal things for the water clouds, which gives the distribution of the all parameters in the vertical sense, and better distribution in the vertical link. And with the geophysics, we've seen that impact where cyclone tracks, other things are improved due to the improvement of the upper echelon circulations, driving forces in the system. And we can see in the case of the cyclone Vayu, we can see the improvement of cyclone tracks with the same initial condition. With with improvement of physics, it is possible to make the changes. And for high resolution, also we started including the urban morphology in the model to get the better sense of the overall urban buildings and urban morphology effects, and like that land cover data, other things in the models, so that to get improve the forecast system. And with that improvement of this new physical schemes, you can see here you can see the improvement in the visibility forecast in the models, and we can definitely see in the surface wind speeds, and also you can see improvements in various parameters with the implementation such schemes. And with these improvements, we can see the model forecast at medium range forecast in India has been improved very much. This figure shows that from the 99 onwards, they show the day 3 forecast improvement compared to the reduction data. You can see the continuously the data we have seen the improvements at various stages, and the color code shows the various model that has been implemented various stages at NCM model. And here you can see the comparison, not only at the comparisons at NCMWF, you can see different international models compared against that various international forecasts such as ECMWF, UK Met Office, and coupled CFSR, and etc. And these comparison carried that NOVA and SEP, and you can see this line, the magenta line showing the NCMWF Indian forecast, that has been very for our tropical regions. They are next to almost in the second position after the ECMWF, and the quality are better than most of the models, and only second to ECMWF. And these improvements are possible due to the various improvements that has been implemented in the models and the simulation systems and data that has been shown earlier. These improvements are led to give a boost to our analysis, our forecast system, and at present, almost our forecast in the tropics, we are the second to only to ECMWF, and further efforts are made to improve the forecast further. And for getting these improvements, we are using many new data sets are being used, and for assimilating the new data sets, we have implemented a strategy by converting the observation system experiments, and also other measures such as FSOE, etc. has been implemented. In OSSC system, what we'll do is when a new observation comes, we'll use that observation. With that observation, run the forecast, and by denying that observation, we'll run the forecast and see how these observations with other physics and other model settings as similar. I can see the impact of the observations and compute the score stats such as this score stat, such as anomaly correlation, RMSE, bias over various regions, such as tropics, shown in the different regions. And we can see whether at various levels, the data is improving over all the regions, many regions such as RSMC region, Northern Hemisphere, and other regions, tropics, etc., how the impact is coming. If you see the green triangle like this, the impact is positive, and if it is red or orange, the impact is negative. And And we can see many observations will help at some regions and may not improve, or such as the blue region where the impact of the virus is not at all there. Like that, we can see various type of observations, how they are how they are giving the forecast, utilizing improving the forecast, whether forecast skill is improved or the forecast is deteriorated. Such type of decisions are taken, and overall, if observations are improving, that observation being used in operational. And another thing, that thing is, we'll see the sensitivity of observation to the forecast. That is called FSOI, in which observations are difference is computed for about a 24 hours period by measuring the deviation for analysis in the background, and this computed for a 24 hours, and see the impact of the how the observations are behaving, whether they are helping the systems. And with this system we are using for the we can see for various time periods, various regions, whether the observation is helping or it is deteriorating, and so that we can make a decision to drop the observation or improve the forecast observation operators to get the better improvement in the forecast. Like that, you can see the comparison of the impact for the years 2021, 2019 for the JJS period. You can see for the areas, observations of satellite observation impact is increasing tremendously, and observations of the conventional observations of the temp and radio temp and other things are not that they improve their contributions or remain same or reducing. And you can see for example, when the new sensors such as Saphir is being used, you can see the improvement that is coming to the Saphir is seen, and with the satellite sensor quality is reducing and the improvement, the contribution of Saphir and on the forecast quality is decreasing, and it became almost neutral, where the sensor has been stopped, the satellite has been taken over from the service. Like that, we can see the impact of various satellite sensors and study it over the period and their usability, etc. And the same thing can be used for judging for developing a new sensor also. And our forecast has been shared with various international agencies for getting to check the quality of that one. We can see clearly compared to the other countries, our forecast has been comparable or even better in various lead centers such as the NCMWF deterministic forecast, and for Japan for probabilistic forecast that we shared, and they're compared from the year to year, and we can see the qualities are compare how good they are, and the improvement is taking place or not. These type of verifications are being computed for testing the various models, and we can see the improvements over the years, and it clearly demonstrates that these improvements over the years. And for the ensemble forecast, you can see that our ensemble forecast systems with JMA we are sharing, and and we can see our forecast quality are almost good enough, and this is the strategy. This is the status of the ensemble forecast systems. And this diagram shows that compared to the comparison between the medium range and short range forecast, that UPS ensemble forecast system improvements from the global deterministic forecast systems. And the above line shows the NCM, the global forecast system, deterministic forecast, and the blue line shows the NEPS, that is ensemble forecasting system for the this for the CRP score. And CRP scores, if it's 0, the quality is good. We expect the model to be near to 0. The quality of the forecast is very usable compared to the other things. Again, you see the red line here that NCMG improvement is that one, and all the prop peaks as 780p, 780 and various levels, 850 mean sea level and winds, 2-meter temperature, all fields can definitely show that ensemble forecast system is much more usable compared to the deterministic forecast in giving the forecast. And the difference between these two systems is increasing as the forecast length for at 240 hours. You can see that ensemble methods are much more better than the deterministic forecast, and hence with this we can definitely show that the ensemble forecast for long range for more than 5 days forecast, the ensemble systems are better than the deterministic forecast. And the same thing, and at present we can see the demonstration of Kerala high rainfall forecast that has been very severe heavy rainfall occurred in over Kerala in the around the mid-May in 2022, and we see these models' performance in identifying heavy rainfall events even at the day 3 levels is better forecasted, and this reliability of the forecast in the even in the extreme cases also are able to catch the and forecast better than previous history, better than expected. It is believed that medium range forecast NWP models for predicting the high level rainfalls, high rainfall events are not that much satisfactory. But in this case, you can see the improvement. We're able to catch the medium range forecast levels. But for resolving the more high rainfall events to the highest level, and this medium forecast to resolution, what we 12 kilometers is not sufficient. So for using the regional models, higher resolution models, we can resolve the events more closely and more precisely to the locations more using the regional models. This is the demonstration with this one. And with this development of the high resolution models and the reliability of the forecasts with compared to global level achieved in the near future, and re-analysis also carried using the system for the both unified models and IMD GFS things for a previous by running the models from the in the case of regional models for about 40 years from 1970 to 2020, and in the case of global models we have the 20 years re-analysis starting from the 1990 to 2018. And we can see how reliable how this re-analysis. We have studied some heat wave cases for during the re-analysis period, and this particular figure shows the heat waves that are identified based on the IMD def and WMO definitions. The heat waves are being identified. How good they are identified. This red line shows minimum temperature, mean temperature, whereas the blue line shows the model from ensemble things, from the radar things, and we are able to identify the heat waves particularly. Number of heat waves, and same way we can see the reputations.
Okay.
We are able to get the best for study the extended range. We are able to get extreme rainfall also well predicted using the Indian DNR set data sets. Hello. Okay. And now in the recent things we are entering the coupled deterministic models also. Coupled models are also with high computing systems are available. We are entering the phase of using coupled atmosphere models or coupled atmosphere ocean models in the predicting the even in the prediction of medium range forecast. Earlier we are using because of the modeling things we are using only for the seasonal sub-seasonal forecast, and now this has been we are able to use the coupled systems for even for the medium range forecast itself, and data assimilation also for the coupled data has been developed for weekly data coupled assimilation and strongly data coupled assimilation or planned, and at present the feasibility of weekly coupled data assimilation is been with the availability of the high computing. The weekly data coupled data assimilation is possible, and in weekly coupled, what we'll do is the assimilations are carried out at they will on their own domains, that is ocean assimilation, and we'll do the atmospheric assimilation, and while running the model, cross-domain impacts has been used in it. And whereas in the strong assimilation, even assimilation stage itself, we'll use the data both ocean and land data together will use that one. But at present, the weekly coupled assimilation is in place, and we have been. This is the schematic diagram of the coupled data assimilation, showing what is the weakly coupled and strongly coupled. As shown earlier, the analysis stage is separate, whereas the strongly coupled systems, both analysis has been used. Observation is used together in the same analysis systems. And at NCMWF, we all a weakly coupled data assimilation system has been tested at by using unified model 11.9 at 10 kilometer resolution, and with soil moisture, also land data assimilation system also in place using the SCAD data soil moisture, and CIS model NEMO and Gaussian model is also in place. With this, the coupled data assimilation has been implemented at NCMWF. This figure shows the comparison between the CAE coupled model and the C and CM means this is a coupled data forecast from the coupled data assimilation system, coupled model system, and then CM is the ensemble forecast system. And you can see the quality of the coupled system is almost similar, and they are almost similar, and gives the confidence that we can use the coupled assimilation, coupled model system for the medium range forecast also. And we can see that the advantage that coupled system is dissolving the rainfall bands much more clearer than the determinist ensemble systems. And the other phase is at in India, at IITM, a new global model has been developed using the dynamical core, TCO dynamical core, and this has been taken from the ECMWF, means based on using the ECMWF type of grades. and we can able to see various resolution that holds that resolution is much more 12 kilometers, 13 kilometers, and at equator levels we are able to get the 6 kilometer resolutions using the T1534 TCO 1534, and with this type of modeling framework has been developed at things, and this show, and for getting this one, various attempts are made. The attempts are made at IITM by first developing the boundary conditions using the planet, land and planet, and using the on their imposing the orography, and we are getting the physics, vegetation, and finally total model has been developed, and this shows the comparison between the TCO grade and T15 1534, and we can see the forecast from the newly developed models are also, they are capturing the probability distribution for the day one day better than, almost equal or better than the GFS system that is operational at present. So it gives the confidence that we can go a 6 kilometer model in the near future. And similarly, at NCMWF also has been developed a 6 kilometer global model, and this is much more running much more computationally efficient and able to complete around with model time take 4 minutes, is much able to complete 1 day forecast in reasonable 2 hours, around 2 hours, and the forecast reliability also. I will show that one. The forecast reliability also much better, and the number of it is using about 200 nodes and run for 5 days, and we can do much. We are getting this from the gidded base of this is shows the what is this? This is OLR from the satellite, all satellite or global satellites OLR data, and this figure shows the OLR generated from the model, and the figure is quite encouraging. The both shows well patterns show are well matching very well, and the features and are very well matched, and this shows encouraging that 6 kilometers the initial runs at what we run at using UK Met Office model and NCM model, the developed NCMWF is encouragement, and you can see this OLR from inside 3D or the Indian region. The patterns are also very well matching. Of course, if we run the model for not many days, it is initial runs only, but the comparison gives the confidence that 6 kilometer model and development at global model development that is taken at NCM model will be good results. With that, we have the confidence that in near future global model we can in India we can go for high resolution 6 kilometer model forecast, and that is medium range can take and it is almost what our regional models are done at that resolution, and within a year or so we are going to run we'll catch global models will be that in the resolution, and we have the scenario that coupled data assimilation also at 10 kilometer runs also possible. So in near future we are going to go high resolution ensemble systems of 6 kilometer and coupled data assimilation models, and will be in place and will go good quality forecast with that one, and with that the we can see the improvement where the course resolution of 150 kilometer, which is started in 1994, and now we are entering a phase where the resolution of the data for global forecast is going to be 6 kilometers, and coupled models also forecast is possible in near future, which gives the confidence that the quality of the forecast, such as tropical cyclones, etc., definitely ocean coupled model will help in the improvement of ocean forecast strength, and because of the ocean forcing also the content in it in that. So with that, I think rosy picture that in near future we are having the better forecast scales, and the block level agro advisory setting what we started in using 12-kilometer models, and with the different deterministic things values. Now the probabilistic forecast also is going to block level forecast, etc. This gives a confidence that in near future India have a better. With this, thank you. Thank you, Guru Subhash.
So, thank you, sir. Thank you, Dr. Prasad, sir, for giving wonderful and knowledgeable talk, especially covering the data types and the use of satellite data for NWP and data assimilation methods, and how NCMRW used NCMRWF used different high computing facilities, as well as the limitations of NWP, etc., and also provided the vision for the future also. And I think we all enjoyed your talk, and I am any questions from the esteemed members, you can unmute and you can. Hello. Hello. Is it audible, sir?
It is audible. Yeah, it
Yeah.
is very much audible. Yeah.
Okay. If any questions are there, please. You can unmute and. Sir, if I am having one question, sir. Actually, in the last slide, in the conclusion part, you have mentioned about the block level forecast. So whether how we can achieve with the accuracy, because accuracy at the block level is the main concern, particularly with the farming system or agriculture system is concerned. How? What about your comments, sir?
No, earlier we are giving the block level forecast by the deterministic models and giving the definite values of the temperature by downscaling the methods. And now by using the ensemble systems and high resolution model, we can give the probability of the rainfall or probability of temperature between how much it will be the decreasing or increasing, these things much more clarity, so that user can take a decision. Instead of telling certain temperature, we can give the temperature about suppose rainfall occurring, temperature decreasing, or it is going to increase, or how much rainfall occur in a percentage sense. So this has been now almost possible now, and it is now used, or it is used in the deterministic sense.
Okay, sir. Okay. Any other questions, please?
evening, sir.
Yeah.
Is there any likely improvement in long range forecast, sir?
The long range forecasts are see, the extended range forecast, we are going to definitely going to come into the into, because we are going to couple models, coupled data assimilation systems and coupled models in with high resolution. The sub-seasonal and extended range forecast going to be improved, that one, and the long range forecast is different ball game, and that improvement was taken elsewhere, not in this is a different ballgame. They are different. That efforts also going on under monsoon mission. MoES is working on, different groups are working that one. That improvement also possible.
Thank you, sir.
Any other questions or comments? Okay, if no questions, then thank you, Dr. V.S. Prasad sir, for giving a wonderful lecture. And also, I am thankful to all our esteemed IMS life members for joining today. This lecture series will continue, and we will inform you the next series, next lecture talk, and soon. And once again, thank you, and also thankful to Dr. Giri as well as Dr. Patnaik sir for providing the facilities from IMD and also from the IMS headquarters. And thank you, one and all.
Thank you.
Thank you. Thank you.
Thank you.